Question 4, we're looking at Charlie the Clown. The clown makes his entrance riding on a cart pulled by Hannah. The clown and cart have a combined mass of 85 kilograms. The handle of the cart makes an angle of 30 degrees to the horizontal as shown in the diagram below. Hannah applies a force of 55 newtons to the handle. A. Calculate the size of the horizontal component of the force on the handle. So we're after, there's a tension force acting along this way. We're after the horizontal component right here. So if that's 55, not 15, 55, then the horizontal component of the force will be, if H for F horizontal, will be 55 cosine of 30 degrees. Because cos the angle equals adjacent over hypotenuse, which is 55, so rearrange that. Anyway, B. The cart is in equilibrium. State what equilibrium means. I'm going to do these point by point. State what equilibrium means in terms of the forces acting. The sum of the forces is equal to 0. That means the net force is 0. That means all of the up forces and all the down forces cancel, all the left forces, right forces cancel, all the forward and back forces cancel. 3 dimensions. And if you're also considering torque, all the sums of the clockwise and anti-clockwise torques as 0 too. Next point, so it's done. Next point, describe what it tells you about the velocity of the cart. Well, if the force is 0 from F equals ma, we know the acceleration equals 0, so that means the velocity is constant. We don't know if it is equal to 0 or not. It doesn't really matter. So it's just a constant, 0 or non-zero. Doesn't matter, constant velocity. On the diagram above, draw labelled arrows showing the direction of any non-vertical forces acting on Hannah. Now this one is a wee bit tricky. Okay, just bear in mind that we're after the vertical forces acting on Hannah. So not the forces she is applying, but the forces acting on her. So the best way to look at this, I think, is the points where forces are acting. So she's pulling on the rope here, and there's also the friction going on here. I think we can ignore air resistance. We can ignore gravity because that's a vertical force. So anyway, there's a horizontal component of the force that Hannah is pulling, which we calculated above. There is a force return to that, which is, because remember all the forces have to be balanced, and this is the tension force from the rope that is pulling back on her, because tension force acts in both directions. Otherwise you would have unbalanced force. Okay. If you just had a single mass hanging on a rope. The other point, the friction, Hannah is pushing against the floor in this direction, and the floor is pushing back in this direction. Think really carefully about that. Push your foot into the floor now. Try and push it backwards, and then, without it letting it move. The floor is pushing backwards in a forward. Change that. The floor is pushing back on you in a forwards direction, the opposite direction to which you're trying to move. That's what friction does. It acts in the opposite direction of attempted motion. So, yeah, remember, as I said, we're looking at the forces that are acting on Hannah, not the forces that she is acting on other things. So we can ignore this one, and we can ignore this one, the force that she is pushing onto the floor, and the force that she is pulling on the rope. There's the tension force on the rope, and there is the friction force on the floor. And what we really should do is label those. In fact, it says it label them. So this is the horizontal tension force, Ft. Let's write it rather than just capital T, pulling on her, and this one here is friction. Now, if we're being slightly clever, we would see that these force pairs, we can kind of ignore them, and there is a tension through her body that is helping to transfer the push from the friction and the pull from the rope that is balancing it all out. Okay, but these force pairs exist, it's true. There you go, tricky one, very interesting one.